Welcome back to the deep dive. Today we're putting on our developer hats, grabbing our text editors, and executing a mission. We're building a custom server, specifically using Python for something called the Micro Content Protocol, or MCP. Our goal here is to get you the essential architecture and the full development roadmap, going straight from environment setup to a working client interaction.
Yeah, this is a fantastic set of sources we have. They would really map out the whole technical structure you'd need for a high-performance, very specialized application like this. But before we get into the code, we should probably clarify what we even mean by MCP, because you're building this server to handle micro-content.
Exactly. Yeah, we can't just throw an acronym like that out there. What is this Micro Content Protocol? I mean, why do we need a whole custom server just for it?
Well, if you think about traditional servers, they're often delivering, large documents, entire web pages, big data packets. Micro-content is the opposite. It's highly structured, it's concise, and it's very, very contextualized data snippets. Think of it like a specialized answer or a single fact, maybe synthesized by an LLM, that has to be delivered with almost zero latency and maximum precision. So the MCP, the protocol itself, just defines the format and the rules for managing those tiny, precise exchanges. It's built for speed and structure, not bulk.
Okay, that immediately grounds the conversation. If the data itself is all about precision and speed, then the architecture better reflect that. So let's unpack this. We've got an MCP client talking to an MCP server. But what's going on inside that server? What are the inner workings?
Right, the server is the intelligence hub. It's not just, passing information along, it's synthesizing it. And internally, it has to connect to several crucial systems to actually generate that microcontent. We can break these down into three main functional categories.
I find this layered structure really fascinating. It tells you right away this isn't just about serving static files.
Yeah.
So where do we start? The data layer.
Right. So first, you have your external resources. This is your traditional data layer. Think databases, document repositories, file systems. This is the raw material the server draws from. The server is really just the intermediary fetching and structuring it.
Okay, so the resources provide the what? What gives it the how?
Yeah.
The ability to execute logic or talk to other services.
That's the second component, tools. The tools integrate external programs and agent-based systems. So if the server needs to, say, calculate a financial metric or hit a third-party weather API or run some complex model that isn't part of its own code, a tool handles that. They extend the server's reach.
So we have resources, the data, and tools, the functions. The third component, though, this feels like where the system gets its real intelligence, especially with synthesized output.
That would be the predefined prompts. This is non-negotiable, really. Since a key part of this architecture is often integrating large language models, LLMs, to generate the content, these prompts are the scaffolding. They guide the LLM, making sure the response is not only accurate, but also formatted correctly and is contextually right for the request.
What's fascinating here is that this whole ecosystem is built around these three things: resources, tools, and prompts. How do they actually integrate with the Python server? Is it just linked libraries, or what's the mechanism?
The mechanism is standardized. It's very intentional. API calls. Everything. Fetching data from resources, executing tools, and interacting with that prompt-driven LLM. It all happens through API calls that are routed through the main server.
Hold on, but why API calls? If you're building a specialized Python server, wouldn't it be faster to just, make a direct database connection or import Python modules for the tools? Doesn't relying on external API endpoints add latency?
That's a really important question. But the architecture here is prioritizing structure and scalability over that tiny latency gain from local imports. By forcing everything through standardized API calls, you get this crucial decoupling. You can swap out your database technology without ever touching the server's core logic. You can scale your tools out as a separate microservices. This layered approach keeps the MCP server itself lean. It just acts as a router and an orchestrator. It's a design choice for long-term stability and modularity, which you absolutely need for a protocol like this.
That makes perfect sense. The server is the conductor, not every musician in the orchestra. It just manages the flow. That dynamic capability is key. Okay, now that we have the blueprint, we have to start building. Where does the rubber meet the road with the actual code?
You need to set the stage. The very first step for you, the builder, is just making sure the prerequisites are in place. This means installing the MCP Python SDK. This SDK gives you the specific classes and methods you'll need to define resources and tools in a way the server understands. Then, once the SDK is installed, you configure your other dependencies, environment variables for API keys, database drivers. It's all just prep work to get you ready for development.
Get the framework ready before you write any custom logic. A developer's mantra. Okay, here's where it gets really interesting. Now we're moving into the core build stages, the actual nuts and bolts of the server. After we've configured the environment, what does the basic code structure look like?
So we immediately established the basic server setup. This means defining the overall structure, handling some initial routing, just basic boilerplate. But critically, you need to choose an infrastructure that respects the protocol's need for high performance. The sources are really clear about adopting fast MCP and async IO right from this foundational stage.
Okay, FastMCP gives us the MCP-specific structure, but let's drill down on async IO. Why is an asynchronous concurrency engine so crucial here, especially for microcontent?
Think back to all those API calls we just talked about. The MCP server is defined by its need to talk to external things. Databases, APIs, LLM endpoints. All of those interactions involve waiting for data to travel over a network. If we used synchronous blocking operations, the whole server would just grind to a halt every time it waited for a database query to come back.
A classic developer bottleneck.
Precisely, and async IO solves this. It lets the server start a network request, say, asking a tool to run a function, and then immediately switch context to handle the next client request while it waits. It's non-blocking IO. For a server like this, it's not just an optimization, it's an absolute requirement to scale to any kind of production load.
So FastMCP for the protocol structure, async IO for the concurrency to manage all those external requests.
Okay.
Once that asynchronous skeleton is in place, we need the plumbing, the helper functions. What's their role?
The helper functions are the utilities. They make the whole server manageable. They handle the internal mechanics of MCP operations. So for instance, they'll handle formatting input data to meet the protocol standards, or parsing complex JSON output from an external tool, or managing connections. They just streamline everything and keep the core logic clean.
And I'm guessing these helper functions, since they're often dealing with input-output, they also lean heavily on that same asynchronous philosophy.
They have to, absolutely. If a helper function needs to retrieve a config file over a network, it must use async IO to do that fetch without blocking. You maintain that continuity. The concurrency engine powers the core loop and all the utility functions that support it. It ensures everything is efficient.
Okay, we've got the structure, we've got the utilities, now we need the brain, the custom intelligence. This brings us to implementing the MCP tool. You said earlier this is the heart of the server. How does the SDK actually turn our custom logic into a functional MCP tool?
This is the most critical stage of the build. When you create the MCP tool, you're essentially defining an interface that the fast MCP framework can understand. The MCP Python SDK gives you base classes or decorators that you wrap your custom Python functions with. By using the SDK's tool classes, you're telling the framework, hey, this is a specific function that knows how to talk to an external system and process the data.
So the SDK is like a translator, turning raw Python into a standardized tool object the server knows how to route requests to.
Exactly. And within that tool, you write your specific logic. Error handling for API failures, transforming raw data from a database into the micro-content structure, and crucially, managing the integration with the predefined prompts.
Right, let's pull the prompts back in here. If the tool has fetched data and run a function, how does it use the prompt to guide the final LLM output to make sure that micro-content structure is followed?
The prompt is the explicit output contract. When the tool makes the LLM call, it sends the raw data it collected along with that predefined prompt. That prompt tells the LLM, I need an answer based on this data, but it must be formatted as a JSON snippet with these 3 specific keys, and the tone must be informative. The tool then gets that structured response back, processes it one final time, and formats it so it can be sent back to the client via the MCP protocol. The tool enforces the prompt's instructions.
It sounds like the tool implementation is where performance really matters, given it has that triple responsibility: fetching, executing, and managing the prompt. Once that logic is baked in, what's the last step before deployment?
That's the optimization and configuration phase. You have to configure the server to run efficiently. This means fine-tuning the server routing in fast MCP and managing the concurrency scaling parameters for async IO. You're basically tuning the whole thing to handle hundreds or thousands of concurrent requests that are all waiting on external APIs. This stage just ensures the server meets the performance needs of the protocol.
We've gone from installing the SDK to setting up the non-blocking backbone with fast MCP and async IO to implementing the core tool. Now for the payoff: calling the server from a client. How do we make sure this whole complex thing actually works?
We move to the final integration step. The client side needs to talk to this custom HTTP server. The source material is specific here. It mentions using the popular request library for this.
Wait a minute. We spent all this time building this super fast asynchronous server with Asyncio, but the client is using the synchronous request library. Doesn't that kind of negate some of the performance benefits?
That's a good point to raise. And it really highlights the difference between server design and, say, client testing. For a simple integration test, or if the client app itself isn't dealing with massive concurrency, the synchronous requests library is reliable, everyone understands it, and it's simple for sending that first POST request. Now, a production client might eventually use an async library like HTTPX to match the server's efficiency, sure. But using requests here just confirms the essential communication loop works. The client sends a request, the server does its thing, and the structured response comes back. It's the simplest way to validate the pipeline.
That makes sense. Keep the initial test simple. Focus on the integrity of the data transmission. That's a clean loop. We've covered everything from the architectural vision right down to a simple HTTP request.
So what does this all mean? We've successfully traced the whole journey. From the Python SDK install and dependencies, through the robust async server with fast MCP and Asyncio, to the final execution of logic in the MCP tool. The key takeaway is really understanding the orchestration. The server is just the router. The value is in the three components it orchestrates: the resources, the external tools, and those predefined prompts.
It truly is a holistic, layered system. We started with understanding the decoupling from API calls, we drilled into Asyncio as the concurrency engine, and we finished with a client connection using a standard library like requests.
A complete operational view of a pretty specialized architecture.
Before we wrap up, let's circle back to what we call the core intelligence, those predefined prompts. We've established the entire server relies on them to guide the LLM's response. So if the build steps, the SDK, FastMCP, Asyncio, if they provide the standard foundation for speed and stability, where does the unique specialized value for a custom application actually come from?
It emerges entirely from the prompt engineering. The structure lets you deliver specialized content quickly, sure, but the quality and customization of those prompts determines the nature of that content. A poorly customized prompt is going to give you generic, unusable micro-content, even on the fastest server. If you want this architecture to provide truly novel applications, say synthesizing legal summaries or highly specific chemical safety data, the time you spend customizing those prompts, making them specific to the data and structured for maximum utility, that's the only way you unlock that specialized capability. It's the difference between a generic template and a highly specialized engine.
Something to ponder as you start defining those specific prompts for your custom tools. That's all the time we have for this deep dive. Thank you for joining us.